So hello and welcome to December 1st. It is now December 2020. This is the last December 1st, 2020 that will ever happen. Do you guys realize that? It'll never happen again. Unless, of course, there's like a new Jesus character and we make a new calendar and eventually there is a December 1st, 2020, which is always possible. But assuming that does not occur, this is the very last one.
Let's stay on topic, please.
Okay, sorry. It is now the 15th week and we are at our first lecture of week number 15. And we are going to do our last session today. And this one is going to be on confidence intervals. Okay. Margin of error, confidence intervals, margin of error, because they are very closely related. And it's essentially the idea of the following. Okay, the last section that we did was on hypothesis testing. And hypothesis testing, testing of significance, is the idea that we go into a scenario thinking that a value has a certain, thinking that a parameter has a certain value, like an average or a proportion. And then we test it. We take a sample and we see whether or not our sample conforms with our beliefs. Did we get a result that is plausible based upon our beliefs, or do we not get a result that's plausible based upon our beliefs? That's what the last chapter was all about. This chapter is a little different. This chapter, we're going in saying, I have no idea what the value is. What I would like to have is a range of values that I am confident the parameter is going to fall in there. And we call that a confidence interval. Okay, it's an interval, it's a range of values that I have a certain level of confidence, a certain level of belief that my parameter falls in there. So let's take a look at this first example. A Rasmussen survey, I have no idea if I pronounced that correct, but a Rasmussen survey found that 59% of American adults say it's important for young people to go to summer camp. The survey did not ask all American adults. It only asked 1,000. So is the value of 59% necessarily going to be the correct value if we asked every single American? No. But chances are it's going to be close because it's a pretty large sample. And they reported the margin of sampling error is plus or minus 3 percentage points with a 95% level of confidence. And what they mean by that is even though the survey itself found a value of 59%, we can only say with 95% confidence that the true value of all Americans is between what two values? If we got 59% with a plus or minus 3 percentage points margin of error, then between what two values will we be 95% confident that the true value falls in?
Between 95 and 100?
No. We got 59%. That's what we got. That's our sample, right?
Oh.
So it's got to be somewhere near 59%. So, yeah,
56%, 62%?
Yes, we go down and up 3%. So when we say plus or minus 3%, we say from 59, which is our actual value, minus 3% to plus 3%. It's somewhere between 56% and 62%. 3% down, 3% up. I am 95% confident that's a true value of American adults who believe that it's important for young people to go to summer camp is between 56% and 62%. The question is, where do they get this plus or minus 3 percentage points from? We call that, by the way, the margin of error. The margin of error here is 3 percentage points. Okay, we don't know the true value, but we are very confident, 95% confident that we know it up into 3% in either direction. That quantity, 3%, is called the margin of error. Now, obviously, if you were going to perform an experiment, would you want a big margin of error or would you want a small margin of error?
Small.
You'd want a smaller one, right? So the question is, what can I do to make it a smaller margin of error? You can only answer that question if you understand where the margin of error comes from mathematically. Then we can look at each part of it and say, okay, I can make this one this, I can do this one to this, I can make this one bigger, I can make this one smaller, whatever you got to do to affect the margin of error. Let's see where we go with this. Okay, so for the summer camp survey, let's fill in the values here. First, what was the sample size? How many people did we ask in our sample?
1,000.
1,000, right? So N is 1,000. What is the proportion of yeses in the sample?
59%.
9%.
59%.
So is that 0.9 or just 59%?
You can write it as either 0.59 or 59%. Mathematically, they are the same. Okay. And how many yeses were there in the sample? How many yeses were there in the sample?
1%.
How much?
Oh, wait.
How many actual yeses were there in the sample?
95%.
No.
59%.
That's the percentage, but how many actually were there? We asked 1,000 people. How many actually said yes?
More than 500. Like,
Yes, it is more than 500. So I'm asking how much.
well, let me pull up my handy dandy calculator.
You don't need a handy dandy calculator for this one. What's 59% of 1,000?
There you go, Wendy.
Oh,
I feel even
590.
before I look, I
Duh.
feel this is going to be our P name. Oh,
I looked at the chat.
so the answer is 590. Wendy, congratulations, 590.
I said it.
Who said it?
I did too.
I didn't hear you because I was ignoring you, so I apologize. Okay. Now, in this context, what is P, the unknown population proportion that is being estimated? In the last example, in the one that we did with, in the example that we did with the hypothesis testing, we went into each problem with a belief of what our value was. And then we tested, did what we get agree with our belief? With confidence intervals, we do not go into the problem with a belief. We don't have a P. So when it says, what is the unknown population proportion that is being estimated, we don't have a number for this. It's just the proportion of all Americans who think young people should go to summer camp. But I don't have a value for that. Because with confidence intervals, we don't come in with a value. We're trying to determine the value. So we have no idea what it is. Okay, hypothesis testing, we had it. Confidence intervals, we do not. So in the survey about summer camp, each number between 56% to 62% is a plausible value for the unknown population proportion P. And these plausible values make up a 95% confidence interval for P, which we could also write as 59% plus or minus 3%. You can either write it as 56 to 62% or 59 plus or minus 3%. At the end of the day, those are saying the same things. This version here gives me the left bound and the right bound. And this version here gives me the center and the margin of error. Right? Left bound to right bound, the center is 59. The margin of error is 3%. Okay, so we do not know P, but we are 95% confident that it is between 56% and 62%. Does that seem reasonable based upon this? Well, let's take a look. Here what we did, like we did last chapter, is we went ahead and we took samples of size 1,000, like our sample, and we did it with an underlying belief that the true value was 70%. Now, in our example that we were given, there's no reason why we should assume it's 70%. But let's just take a look at whether or not 70% is a plausible result. If 70% is a plausible result, how often will we get 590?
Looks like 0. Well, we don't know because it's not on.
Yeah,
Wow.
well, basically 590 is like over here somewhere, right?
Right.
590 is such an implausible result that it will essentially never happen if P was really 0.7. This is going back to what we did last time. So 0.7 is very implausible. And if we look at our data, our conclusion is that it's somewhere between these two, right? That was our conclusion, right? Our confidence interval was from 56% to 62%, right? Well, if it's from 56% to 62%, 70% is not in there, is it?
Right.
70% is an implausible value. 70% does not jive with our results from our experiment, which was 590 yeses. So this connects the confidence intervals that we're doing now to the hypothesis testing that we did before. So here's a new one. And in this one, we created another distribution, again, samples the size of 1,000 to match ours. But this time we said, what if P was really 0.58? If P was really 0.58, is 590 a plausible result now? Oh, certainly, right? 590 occurred roughly, right? 590 is right around here. It occurred roughly 2% of the time. Now you might say 2%, that's not really quite often, but even the highest was only 2.5% of the time, right? So it was very close in percentage to the most plausible value, which is 580. So 58 is certainly a reasonable estimate. And in fact, if we go to our confidence interval, is 58% a reasonable value?
Yes.
It falls right in our confidence interval. So because it falls right in our confidence interval, it's reasonable. And again, we see that the confidence interval approach and the significance testing approach match up again. So to decide if a proportion is a plausible value for the unknown, we can construct a sampling distribution for the number of yeses from samples of that size. If the result falls in the middle 95%, then it is a plausible value. So in our case, 0.58 was a plausible value because 590 came in the middle 95%, but 0.7 was not a plausible value because 590 was not in the middle 95%. In the confidence interval approach, I can immediately tell that answer. I don't need to make my sampling distribution. 70 is out and 58 is in. So in that sense, confidence intervals are a little bit easier. Okay, so let's read this definition of the Common Core definition of margin of error, or what students need to know in Algebra 2. We need to take data from a sample survey to estimate a population mean or proportion. We've been basically doing proportions, but you can do it with means as well. And then we need to develop a margin of error through the use of simulation models for random sampling. So we have to figure out the margin of error. So let's do it for the following activity. A study of 40 kleptomaniacs. Everyone here knows what a kleptomaniac is?
Yes.
Yeah, kleptomaniac, someone who loves to steal things. A study of 40 kleptomaniacs found that 14 had onset of the behavior before age 11. So let's fill in the values. First, what is the sample size?
40.
40. What is the proportion that said yes? And how many?
14.
And how many said yes?
14.
No, 14 is the number who said yes, right? 14 is the number who said yes. But what is the proportion who said yes?
Oh.
14 out of 40.
14 out of 40, which is what?
I don't have my calculator ready.
0.35.
0.35. So 35% was the proportion who said yes. What is the unknown population proportion that is being estimated? Again, we don't have a number for this. We just basically can only talk about it conceptually. It's the true value of the proportion of kleptomania, it's the proportion of kleptomaniacs that had onset behavior before age 11. Now,
What was
we
X
have
again?
no idea what P is. We have no idea what P is.
No, what was
Let's
X
take-
again?
Sorry?
X again?
35%.
No, P hat is 35%.
P
X,
is 35.
X is 14.
14.
Oh, I
That's
wrote
what
that in the
thought.
wrong spot.
Right?
Okay, thank you.
So let's take a look at these two, or these six. Notice what is the what are the size of my samples in all 6 of these graphs, or 8 of these graphs, or 10 of these graphs, or 12 of these graphs. Wow. In all 12 of these graphs, what is the size of my sample in all of them?
40.
Every one of them is 40, because otherwise, how can you compare it to our sample, which is 40? They have to be the same sample size. Otherwise, you can't make a valid comparison. So every one of these is 40. Now, this is when P is 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5, 0.55, 0.6, 0.65. So these are all different ones. Let's see which of them give us a plausible result of 14 yeses. Okay, let's look at the first 6. Is 14 plausible in the first result?
No.
No, because 14 is way out here. This one's out. Is 14 a plausible result in the second one?
No.
Well, it's not in the middle 95%. Is 14 plausible for this one?
No.
Still probably not. It's still way out here. So let's say it's not, but we're getting very close. Is 14 a plausible result here?
Which one are you pointing at?
The fourth one.
Oh,
Is 14 a
no,
plausible?
because wouldn't it have to be between the 10 and the 5?
No, it's the middle 95%. The middle 95% is probably like that much. Is 14 in the middle 95%?
No.
That's right here. What do you mean? This bar here.
Oh,
is
I see
14.
the arrow. Wait a minute. I got to write that down.
Yeah, I would think this is a valid. I think that's plausible. It's 5%. 5% is pretty plausible. How about 0.3? Is 14 plausible here? Here's 14. Is that a plausible result for this one?
Yes.
Yeah. How about this one? Is 14 a plausible result for this one?
Yeah.
Oh, certainly. It's right in the middle. How about these ones? Let's cross these out because they're getting in the way. Is 14 a plausible result for this one?
Yes.
Yeah. Is 14 plausible for this one?
No.
14 is still pretty high. That's still 6%. That's still pretty plausible. How about this one? Is 14 plausible here?
No.
Huh? 14 is here, right? Is that within the middle of 95%? Borderline. That's probably like the boundary. How about here? Is 14 plausible here?
No.
No, 14 is probably not plausible there. How about here? Is 14 plausible?
Nope.
No, certainly not. How about here? Is 14 plausible?
No.
Not at all.
That's not even on it. So that's all out. Okay. So it looks like the plausible values are from, this was like a boundary. Like 0.2 is probably like the very edge. So like 0.2 to 0.5. So if I had to make a confidence interval here,
Where did you get the 0.5? Which one were you looking at? It's so small on my
Point-
screen. Sorry.
0.5 is this one.
0.5. 0.2 to 0.5.
Yeah, so I would say 0.2 to 0.5 are the values of P for which a result of 14 is plausible. Does that make sense how we did that? We went through all these different ones. And we picked the ones for which 14 is a plausible result. What we get is the values of P between 0.2 and 0.5. So that would be my confidence interval. Now, this is not the way that you normally do it. There's formulas for getting confidence intervals. Okay, in fact, even though we haven't learned those formulas, and it looks like we're not really going to learn them, what I can do here, I mean, I happen to know the formula, so let's actually, let me write it out, and then we can evaluate it. Okay, so the formula is as follows. The formula is, you can write this down if you want, p hat, that's the value that we actually got, plus or minus the square root of p hat times 1 minus p hat over n, and in front should be this thing called z star. Again, we're not going to learn these details, but I am curious what the actual values are. So in our case, what was our p hat? What was our sample value? It was 0.35, correct? Yes?
0.35 p hat, yes.
Okay, and without going into the reasons why, for 95%, z star is 1.96. Not going into the reasons why, just trust me on that one. So we get 1.96. P hat is 0.35. 1 minus p hat is then 0.65. And then when we divide by n was what, a 40? Correct?
And it's the total sample, yeah.
So 0.35 times 0.65 divided by 40. We take the square root of that. We multiply it by 1.96. So I get 0.35 plus or minus 0.1478. We'll just say plus or minus 0.15, which gives us 0.20 to 0.50. And what did I say was the confidence interval based upon these graphs? Approximately
0.2, between 0.2 and 0.5.
0.2 and 0.5. So we don't have this formula, but it does show that these graphs do seem to conform with the formula, which is really nice. So let's now go down to this one here. Okay. The last Gallup poll before the 2012 presidential election predicted that Obama would get 49% of the votes. The poll of 2,700 likely voters gave a margin of error of 2%. So if we say 49% plus or minus 2%, what does that mean? 49% plus or minus 2%.
It's in between 47% and 51.
Between 47% and 51%.
With a 95% confidence.
It actually does not say 95% confidence, does it?
I'm just kidding. I was trying to get extra points.
Oh, well, unfortunately, you lost them. Now, Obama actually got.
That never happened.
Sorry, what was that? What?
Just the last minute never happened.
I believe you. Okay. So Obama actually got 50.6%.
Oh, you know what? I was reading the bottom thing. That's why.
I see. Okay, fair enough. So I'll give you those points back after all. Okay.
Thank you. I appreciate that.
You're welcome. So Obama actually got 50.6% of the vote. Was this within the margin of error?
According to Angela, yes.
According to Angela, and
wasn't it between there?
Well, someone said 47 to 51, correct?
Yes.
Is 50.6 within there?
That's what I said.
Yeah. Okay. Not because of Angela. She didn't do anything.
She said that. She said that.
Thank you, Lori. You're my biggest supporter.
Oh my gosh. It's like
sorry, I thought it was someone else. I'm sorry. Anyways, okay. Now, the last Fox News poll before the 2016 election had a 95% confidence interval for the percentage of the vote that Trump would receive of 41.5% to 46.5%, much lower. What was P hat in his example? We do love Lori. She's the best. I mean, second,
Aw.
I'm really the best, but after me is Lori. Angela's way down the list. I'm just saying. So what is
Don't be
P hat?
mean.
What is P hat for that example?
41.5 to 46.5.
Well, that's the mark. That's the confidence interval, right? 41.5 to 46.5. P hat is right in the middle,
Right in the middle.
in the center. So what is right in the middle of 41.5 to 46.5? What's right in the middle of 41.5 to 46.5?
43.5?
Try again.
0.75?
Try again.
44?
44%. So P hat was 44%. What was the margin of error?
41.5 to 46.5.
Well, the margin of error is a number, right?
Plus or minus 5?
Plus or minus. No, you don't go up 5 and down 5. The total range is 5. So what's the margin of error? How much do we add and subtract? How much?
2?
Not 2.
I want to say 10.
Definitely not 10. What's 41? Go
Oh,
40,
no.
go
2.5.
41.5 to 46.5 and
Yeah,
divide it by
okay,
2.
my bad.
So 5 point,
2.5.
yeah, 2.5.
2.5%. The margin of error is 2.5%. Now, he actually got 46.1% of the vote. Was this within the margin of error?
Yes.
Yes, it was. So both of them were within the margin of error, which is always nice when polls conform with reality. Now, can I estimate the margin of errors with a simple formula? And the answer is yes, kind of, a little bit. I gave you a formula a few pages back, which is probably gone by now. So I'll rewrite it again. The margin of error that I gave you, the plus or minus part, was this number Z star, which is 1.96 for 95%, times the square root of P hat 1 minus P hat over N. This course is saying, let's make it just simpler. Forget about this whole Z star and P hat and 1 minus P hat. Just ignore those and just do over the square root of N part. Because if I actually do 0.35 times 0.65, take the square root of that and multiply by 1.96 like I did in the last example. Do you know what I actually got for that? I got 0.94, which is pretty close to 1. I actually got something pretty close to 1 anyways. So this formula here is a nice, simpler estimation of the margin of error. 1 over the square root of n. If you do 1 over the square root of n, and you take that value, that is a nice little approximation for the margin of error. 1 over the square root of n. So let's apply it to a few examples. In the first survey that we did of 1,000 American adults about the kids going to summer camp, we got a margin of error of what? 3%, correct? Isn't that what we got if we go all the way back to the very beginning? Didn't it say 3%? So let's take a look at what this formula gives us for the margin of error. All we got to do is do 1 over the square root of 1,000. What's 1 over the square root of 1,000? What's 1 over the square root of 1,000? Anyone?
I don't think, oh, now it's working. 1 over square root of 1,000.
0.03. Oh, you wrote it. Never mind.
Right. And by the way, just so you know, if I use the exact formula, I get that, which is not really that bad. All right. It's not, I mean, if you're going to round anyways to 2 decimals, you're going to get the same answer. It's not really a bad approximation. Even though I would always say, why use an approximation if we have the exact formula? And we did it for 40. We already did that one, right? We got, right, 1 over the square root of 40, that other example. We got, 0.16% or something like that, which is very close to the 15% that I did in the formula. But now we have a question which is a little different. Suppose you go into the problem and you say, you know what, guys? I want my sample to be so big that my margin of error is only 4%. The question is, how big of a sample do you need to ensure that your margin of error is only 4%? So what we do is we first start with the formula. The formula says that the margin of error is approximately equal to 1 over the square root of n. Here's an example where I know what my margin of error is, and I want to figure out what my n is. So what is my margin of error for this problem?
4%.
4%. So I get 0.04 is equal to 1 over the square root of n. And then how do I solve for n?
Divide both sides by square root of n.
You
No.
have to get rid of the square root first, but I
Yes.
forgot what you do.
How do you get rid of a square root?
Just to square, to
Oh, multiply
unsquare
both
it.
sides. I'm sorry.
Square both sides. If you
Square both
If you
sides.
square both sides, now you've gotten rid of the square root, but we still haven't solved for n. So how do I get n?
Just multiply the other side by n. No,
If I multiply both sides by n,
They cancel each other out.
then those cancel. And I now have 0.04 squared, which is 0.0016n is equal to 1. And then what's the last thing I do to get n by itself?
divide by 0.0016.
Divide by 0.0016, and that gives me 625. So if I'm going into this problem and I'm saying I want my margin of error to be no more than 4%, then I would make sure not to take a sample smaller than 625. David, do you have a question?
Yeah, I thought we got rid of the square when we got rid of the square root. So it should only be n times 0.04, no?
No, we square both
You
sides.
still have the square.
You square the left, you square the right.
Yeah, but
squaring the right gets rid of the radical, but squaring the left, you still got to square it.
Ah, okay. Gotcha.
All right,
Yeah, I confused myself. Thank you.
no problem. Yeah, okay, so we just did that one. Okay, so let's go back again and understand exactly what we mean by a 95% confidence interval. What we really mean by that is if you take lots and lots and lots and lots of samples and we compute a 95% confidence interval from each of those samples, 95% of them will capture P. In other words, P will fall in 95% of my confidence intervals. And P will not fall in 5% of my confidence intervals. That's really what we mean by a 95% confidence interval. But the way we really mentally think about it is how confident we are that any one specific interval has captured P. If I have an interval from 47 to 51, and it's a 95% confidence interval, I am 95% confident that this interval has captured the true value. Is it in the middle? Is it towards the left? Is it towards the right? That's a whole nother question. I can't answer that question. I don't know. These are all the plausible values. No one of them is more plausible than anything else. Okay? So I want to skip this one because I don't want to do that. I don't want to do this. Okay, let's do this one here. A Harris poll conducted online with 2016 adult Americans found that 21% said that they had some sort of tattoo. Fill in the values that correspond to each symbol. First, what is my sample size here?
2016.
2016. What are the proportions who said yes in the sample?
21%.
21%. How many said yes in the sample?
$423.
That's what I get, 423. Describe, don't give me a number because you can't, but describe P, the unknown population proportion that is being estimated in words. In words, what is P?
In words, what is P?
In words, what is P? P is the true proportion of Americans that have some sort of tattoo.
So is the reason that it's asking us to describe it is because we wouldn't know it unless we looked for it?
Yeah, that's right. We have no information going into the problem for what it might be. We're not testing to see if some value is correct, like we were for significance tests. We have no idea what it is, but I know conceptually what it is. It's a true value. I don't know what it is, but I know what it is. You know, I mean, I don't know the value for it, but I know what it is. It's the true value, whatever that is. Now, here's an interesting question. It says, what must be true before you can compute the margin of error? This actually gave me a second or two to think about it. What must be true before you can compute the margin of error? The answer is you have to make sure that it's a good sample. Online samples are generally bad because only people who are invested in the idea tend to be the ones to actually respond. But a tattoo example, it's kind of like a yes or no. Why would people lie about that? Why would you lie about having it? I mean, who cares? Like, some people have, some people don't. It's like, oh, I'm not going to tell the truth here, so I'm going to lie. Like, I don't see why people would necessarily. If you don't want to say what it is, then don't do it. However, maybe people with tattoos are more likely to respond, and therefore the percentage is higher than it would normally be. I don't know, but you have to make sure that it's a valid sample. But anyways, let's compute the margin of error. Based upon our formula, what is the margin of error? Approximately, at least. What is the margin of error based upon our formula? What is our margin of error?
Based on the formula, you said?
Yep, based upon our formula. We have a formula to compute the margin of error. So based upon that formula, what's the margin of error?
0.02.
I'm going to throw in an extra decimal just for a little completeness, but 0.022, yeah. There's 1 over the square root of 2016. So complete this sentence. We are 95% confident that if 2016 Americans could have been asked, that if all Americans could have been asked, remember, we're looking for the true value. We are 95% confident that if all Americans could have been asked, the percentage who would have said that they have a tattoo falls someplace in the interval what to what. Again, we are 95% confident that if all Americans could have been asked, the percentage who would have said that they have a tattoo would fall someplace in the interval what to what.
20 to 25%. No.
No, where are you getting that from? You're making it up?
No, I was trying to figure out from the estimate, but I was
Well,
figuring it
what is
wrong.
our estimate?
2.2%.
No. That's our margin of error. That's not our estimate. That's our margin of error.
I thought the E means E is approximately, oh, I see. Never mind.
That's the margin of error. So what is our estimate that we had in this problem?
21%.
21%. That's our actual estimate. That's our p hat. This is our margin of error. So what's our interval going to be? From what to what?
18.8 to 23.2.
18.8% to 23.2%. Now, I'm just curious. Hopefully no one's embarrassed if they do have one or do not. But how many people in our class have a tattoo? David, that's 1.
I do.
2. 2 people. So that is significantly lower than 21%. However, it's a very small sample size. Plus, you guys are young, right? Most people who do get tattoos tend not to get them until they're at least 18. I'm not even sure if it's legal to get one before you're 18. It might be, I don't know.
Parent has to be there.
Right.
something
So,
like
you know, there people who get tattoos tend to get them, you know, later, you know, college
16,
age or later.
16 on up to 18 with parents' consent.
Wait, so 16 with a parent's consent? So even under 16, even a parent can't consent?
No, they won't do it. Not in California.
They won't do it. Okay. So yeah, so it could be our samples just, you know, full of mostly younger people. Myself, I'm Jewish, you know, Jews, at least according to my strict beliefs in Judaism, we don't allow ourselves to get tattoos. Some of the more lenient denominations might. I don't know much about them, but there could be religious reasons why people don't, and certainly age reasons. So our sample was very small, and our you know, we certainly don't have a sample of size 2016, right? Our sample is 30 something, much smaller. Now, the confidence intervals that we've done so far have been for proportions. Okay. But they don't have to be for proportions. You can also do confidence intervals for averages, for means. So here's an example. The temperature of a random sample of 65 men was measured and the mean was 98.1 degrees Fahrenheit. A 95% confidence interval for the mean temperature of all men was constructed from the data, and it was 97.9 to 98.3. For a sample of 65 women, the confidence interval was 98.2 to 98.6. Now, growing up, what are you told growing up? Or maybe it's different nowadays, but what was the temperature that we were told growing up was the perfect temperature a person should have if they were healthy?
98.5 or something.
So I was always told 98.6. That's
Or
what,
98.6.
that's what growing up, it was always 98.6, 98.6.
You're right.
Is 98.6 a plausible value for the mean temperature of all men based upon this data?
No.
No. Is it plausible for women?
Yes.
Yes.
It's kind of hard
It's
to
right
say.
at the end.
It's kind of hard to say because it's on the boundary, you know, kind of hard to say, but let's say borderline.
Well, if you're rounding, wouldn't it be 98.6? So
Well, you're not rounding. It's 98.2 to 98.6, right? This is an interval, but we don't include the endpoints.
Oh,
That's why
gotcha.
that's why they're open. They're not brackets. They're parentheses. We don't include them.
So
But
then it's enough.
98.6 is infinitely close, so it's borderline.
Gotcha.
What was the mean temperature of the women in the sample? What was the mean temperature of the women in the sample?
You're looking for the middle, right?
That
Yeah.
was
Looking for the
98.4.
middle. So what is the mean temperature of women in the sample?
Oh wait, 98.4.
98.4. Is this convincing evidence that women are hotter than men? And when I say hotter, I mean temperature-wise. Is this convincing evidence that women are hotter than men?
But somebody was definitely trying to have fun
Yes.
writing this stuff here.
That
Yes.
could very well be. I mean, we don't know the truth of the statement if we think of the word hotter in a different context. But in the context of temperature, is this convincing evidence that women are hotter than men? And the answer is
No,
no.
No.
Why not?
because it's too small of a sample
Small,
size.
Yeah.
No, I mean, even if it was a larger sample size, let's focus on the confidence intervals themselves.
The further right
It's too
interval's
small.
94.3, and the women's average or women's mean sample temperature is 98.4. So it's got that small 0.1%.
Yes, there's an overlap.
Yes.
Overlap.
There's an overlap. These two intervals overlap. And because those overlapping values are plausible for both, it is not convincing evidence that women are hotter than men. Now, Yesenia, if you believe that women are hotter than men, then you can always say, well, let me take a larger sample. It'll be a smaller margin of error, because the larger the sample, 1 over the squared of n, a smaller margin of error. And then hopefully we'll get no overlap, and we can make the claim that women are in fact temperature-wise hotter than men. But with an overlap, you cannot make that claim. In fact, if you go back to this one here, if you think about the Obama survey, when he got 49% of the vote with a margin of error of 2%, that's from what? It's from what values to what values?
41.5 to 46.
No, 47
And 51.
to 51, which means it's more or less than 50%. It could have gone either way because any of those numbers are plausible. So he might have lost or won the popular vote based upon that particular prediction.
So just so I'm clear, going back to the temperature one,
Yeah.
if the numbers are overlapping, then it's not a good sample.
It's not convincing evidence that one is bigger than the other.
Got it.
My two confidence intervals have to be separate. This one has to be all larger than this one for me to say convincingly, I really am convinced that the value for this is bigger than the value for that. But when they overlap, because of the overlapping region, I cannot make that claim.
Okay.
Okay. And that takes us now to the end of chapter 23. And as such, the last chapter that we will be doing in this course. We are now done with the curriculum.
Woohoo! We don't get to see your face anymore. I mean,
That's
oh,
not
I didn't say we're done
nice.
with classes. Jesus. Okay, I said we're done with the curriculum. Wow, that was so insulting, but that's okay because I feel the same way.
Wow.
So that's
but
totally.
you're not even seeing my face, so
I know. What's up with that? Why'd you go
joke's
off?
on you. Because my eyes started crying, so I didn't want to see me cry.
Because you were looking at me too much?
Yeah.
I get that a lot. Okay, that makes sense. By the way, did Patty ever show up? I don't think she did.
They told you to read your emails.
Yeah, but I'm not going to read my emails during class time. That's just unprofessional.